Hi, geometry friends. We have arrived in chapter 11. And chapter 11 is going to be kind of cool because we're going to be talking about areas of parallelograms and triangles. So the first thing we need to do is get some of this vocabulary out the way. And it's not really hard at all. And I think there are concepts that you will be quite familiar with. The first one asks us to consider the idea of the base of a parallelogram. And one could really walk up to a parallelogram and say, hey, here's my base. Just say the bottom one is the base. But what I want you to be able to know is that any side of a parallelogram could really be the base. Even if it's not oriented to look that as such, you could honestly be talking about the base of a parallelogram and it be this side right here. How you determine whether you're dealing with the base of a parallelogram really comes with the next definition, the height of the parallelogram. So the height of the parallelogram, I'm going to highlight in red here, and I am going to change the orientation of this just for drawing purposes. So if I am given, let's try it again, if I am given a parallelogram and I find out the height of the parallelogram, let's say somebody showed me that we were given this information that the perpendicular distance from one side, let me try to make it neat, the perpendicular distance from one side, the base, all the way up to the other side, or contained in the line going through it, right? The extended line going through that particular place. That would be the height. So if you consider, I could have drawn the height from here to here as well, right? Because I'm considering basically, sometimes I don't know, I overtalk this one, but I imagine if the parallelogram could fit through a door, the height of the door would be, imagine the parallelogram sliding on one side and it has to, right? Anybody with me? All right. Hopefully that makes sense. So if you had to slide the parallelogram through the door, how high does the door have to be? So you're not measuring like the slant height or one of these other bases, I'll call it over here. So when we're dealing with a parallelogram and we have a base, we generally make sure that we call the part that is our base, the base if it is clearly the way we get the height, where the height is drawn to. I hope that made sense. That was a bit of a babble, babies, but I hope you get what I'm saying. So these are different representations of the height of a parallelogram, and this is my little door analogy. And honestly, this analogy or this idea follows through with the triangle. So you can have a triangle that is like this, kind of nice and scalene. Scalene being all three sides are of different lengths, and I literally can call any one of these sides the base of the triangle. It really just depends on the information I have and what's most convenient. So this side could be the base, this side could be the base, or even this little bitty side over here could be the base. I'm going to make this little bitty side the base. And so if this is the base of the triangle, and again, remember, it doesn't have to be any particular side, but I'm going to make it this side right now. If this is the base of the triangle, the height of the triangle is going to be the distance from the opposite vertex straight down and perpendicular to either the base or the segment containing the base, or the line containing the base. So here's a line that contains that base, and the height of the triangle is going to be the distance, the perpendicular distance from the vertex opposite the base straight down and forming a perpendicular angle with either the base or the side containing the base. And you guys see what I mean here, right? And so I'm going to, I don't know, maybe I should use gray. I don't know. No, let's not use gray. Let's use a nice deep dark, I don't know, yellow. All right, so there we go. So our yellow height, make a thicker pen, Dion. Our yellow height is that in terms of a triangle. It doesn't always have to be outside of the triangle like this, but I wanted to show you this example so it could be. All right, now that I've really spent a lot of time on that, let's go ahead and get to a bit of information. So you can see some the area addition postulate here is in play. Basically, I really like this. If you think about the area of a parallelogram, it really comes out of kind of making it look like a rectangle. If you were to cut off this side, knowing that all of this is parallel, each of the opposite sides are parallel, if you were to take a perpendicular line and cut this part off, it would fit perfectly onto the other side. And you can see from there that the area of a parallelogram is going to be base times height. So here we have it written neatly. Area is equal to base times height, knowing that the base is one side and the height is always drawn to that base. Let's look at an example. So here we have example 1, and we're asked to find the area and the perimeter and the area of this parallelogram. That's the symbol ABCD. And so given that we have some information we remember about parallelograms, we know this side is 4 inches, we know this side has to be 10 inches. So finding the perimeter is pretty easy. It's going to be 2 times the 4 inches plus the 10 inches, right? And because there's 2 of each, and then so what I get is 14 in here times 2, I'm going to get 28 inches. Not that big a deal. I know you guys can do that. Now we need to talk about what the area is. In order to talk about the area, we need to figure out what height we have, and here we have height of 5, and so we got the base here. So remember, the area of a parallelogram is equal to base times height, and I think you guys got that down pat. You know what the base is, 10. The height would be 5, and so the area is going to be 5 times 10, which is 50. I don't know why my pen just broke down in that way. So we've got 50, and we write inches squared. So I'm going to write it again. 50 inches squared would be our answer. Not too bad. All right, let's look at the next one. Okay, so here in example 2, we're going to find the area of this parallelogram, and the parallelogram is EFGH. And so we look over at the diagram and we see we've got the length of the opposite sides, which is helpful, but we don't have the height. And that's a problem. But we do have this. We have an angle, and so that might help us out. Any ideas what we can do with this? Hopefully you guys are seeing that this angle gives me a triangle right here that we are familiar with. This has to be a 45-45 right triangle. Given that the height is perpendicular, it makes a perpendicular angle with the base. And then these two angles have to add up to 90. If that's 45, that's 45. So we've got this 45-45 right triangle, and we know a bit about it. If you remember from before, when you have this type of a special triangle, we know that the sides, because it's isosceles, let's call those side lengths S, and the hypotenuse will be S times the square root of 2. And so that gives me some indication of what's going on here. So I want the height. The height looks like one of the sides of this isosceles triangle. I've got the hypotenuse. So what I do is I take the hypotenuse, 8.5, and I set it equal to the side times the square root of 2. The next thing I'm going to do is divide both sides by the square root of 2. And now I have the side length. Now I know this isn't the best looking type of problem. I'm going to do what I know how to do. I'm going to fix the look of this without my calculator. I'm going to take 8.5 over the square root of 2, and I'm going to do something called rationalizing the denominator. It's a typical thing we do in math, so we don't have a weird, an irrational number down here, and it makes life a little bit simpler. So I'm going to multiply this fraction by the number 1. But it's a special one. Sometimes I call it a gourmet one. That's going to do the job of rationalizing the denominator. So at the bottom, I've got square root of 2 times square root of 2, which is just 2. And at the top, I've got 8.5 times the square root of 2. And so I could leave my answer like this. I could go a step further and write 4.25 root 2. And I could, of course, calculate what the root 2 is and multiply that in. I'm not going to do that for this example, though. I'm just going to leave it as such. But you certainly could use your calculator to calculate that. So that gives me the height, but that doesn't actually give me the area. So what do? I've got to go back to what I know. The area of a parallelogram is equal to base times height. And that's what I'm going to play off of here. So the base is 15 millimeters. And the height we just calculated as 4.25 times the root 2 millimeters. And now that I've got to multiply this stuff, I think I will pull out my calculator and use it. So I'm going to head over to Desmos, and here I have 15 times 4.25 times the square root of 2, and I get 90.156. So I'm going to go back and just write that down. So this is going to be approximately, this here is going to be approximately 90.156. So let's say 156 would be rounded up to 1.16 millimeters. Make sense? All right, let's try another one. So here we have a quick idea. We've got the base of a triangle and the height, and we have a postulate that just gives us some idea. Area of congruence postulate. If two figures are congruent, then they have the same area. I bet you guys knew that. All right, let's go on. So I'm sure this concept is one that you've had in mind for a really long time, probably since 6th or 7th grade. The base of a triangle, and the height of the triangle are listed as such, and when we want to find the area is 1/2 base times height, or you could write it as base times height over 2. Those are equivalent, and that'll lead us to our next problem. So here we have gardening with DeAndre. DeAndre needs enough mulch to cover the triangular garden shown and enough paving stones to border it. If one bag of mulch covers 12 square feet and one paving stone provides about 4 inches of a border, how many bags of mulch and how many stones does he need? Clearly, this is a veiled way for us to be talking about the perimeter, paving stones around the edge, and the area, the bags of mulch that cover the space, right? So let's go ahead and see if we can get that information. So the perimeter we'll need to find, and we'll need to find the area of the triangle. To find the perimeter, we need to add up all 3 sides, which makes total sense. So we will be adding 23 plus 7 plus 15 feet. When we add up those 3 sides, we get 30 here plus that, we get 45 feet squared. Not squared, just 45 feet, my fault. And then with that 45 feet, we need to calculate how many paving stones we're going to need. And we have 45 feet to cover, but each paving stone only covers 4 inches. So how can we calculate that? What will we have to do? The first thing we should probably do, right, is to figure out how many inches is 45 feet, so we can then divide up these inches by 4. So I would take 45, multiply by 12, and I would get, I'm thinking about 45 as 6 times as, let me think, I'm thinking about 45 as 9 times 5 times 12, so 5 times 12 is 60, and then 60 times 9 is going to be 540, so I've got 540 feet, okay? That kind of makes sense. 45 times 12. No, it doesn't make sense because I don't have 540 feet. I have 540 inches. Thank you. I heard you. I heard you telling me, like, no, lady. Okay, so now that I have these 540 inches, to figure out how many paving stones I need, I'm going to take 540 and divide it by 4. And when I do that, I get 114. It goes in there 3 times with the remainder of 2. Okay, I need 135 paving stones. That wasn't too bad. All right, let's check out the bags of mulch over here. So we need to find the area, and to find the area we need base times height. The base of this triangle is 7 because we were given information about the height. That's going to lead us to the orientation that this is the base. So the area of a triangle is 1/2 base times height, and in this case, that's 1/2 7 times 9. Are you guys with me? I hope this makes sense. And so now we've got 63 over 2, or 31.5 square feet. Now we got to figure out how many bags of mulch we need. So we're going to divide the 31.5 by 12, which isn't too hard to do. We know it goes into there twice, but not quite 3 times. So it goes into there 2 and some change. However, since I'm buying mulch, I'm going to need 3 bags. This next one, we have the height of a triangle is 5 centimeters more than the base. The area of the triangle is given as 52 square centimeters. Using the formula, we put 52 in. We're going to try to find the base and the height. We put 52 in, and we now work 1/2 times b plus 5. We're going to multiply this together by using the distributive property, and then get rid of this 1/2 by multiplying both sides by 2. We have a quadratic here. We solve quadratics by moving everything over to one side and factoring. The only answer that makes sense when I factor is that b has to equal 8, because this would be b is equal to -13. So if b is equal to 8, then the height is equal to 13. And that's how you handle that one. All right, guys, I know that was quick. I didn't want to make 2 videos, so you had a lot to do. Let me know if you have any questions.